Hey everybody. Well, we've been talking about terrestrial planets for quite a while, and we've gotten a lot of details about them, haven't we? But we would be remiss if we didn't also try to get as much information out there about the Jovian planets as we could. Um, but we're not going to talk as much about them as we have. Um, Most of the reason for that is because there's a lot we just still don't know about the Jovian planets. Um, Terrestrial planets are a lot easier to study because A, we live on one, and all we got to do is walk around the Earth. Um, but also because we've only been out to the Jovian planets a few times. Um, the Pioneer 10 and 11 missions were flyby missions that flew by Jupiter and Saturn back in the 70s. Um, Voyager 1 and Voyager 2 were both launched in the late 70s, and Voyager 1 flew by Jupiter and Saturn, and it's currently coasting under its own inertia, coasting its way out of the solar system. Voyager 2, they launched Voyager 2 in 79, I want to say, at just the right time so that it could fly by Jupiter, Saturn, Uranus, and Neptune, and it's also coasting its way out of the solar system right now. So Voyager 1 and Voyager 2 are still alive. They've still got a little bit of juice left in their power supplies. And so we're still keeping in contact with them as best we can. But they've both basically left the solar system in just the last few years. Which, let's think about that for a second. Voyager 1 and Voyager 2 are two of the fastest man-made things ever. The only man-made vehicle, the only man-made object traveling faster than the Voyager probes is the New Horizons probe at the bottom of that list. Okay? These are the fastest man-made things ever. We launched them on the biggest rockets that humanity makes. And they've taken 40 years just to leave our solar system. So, that basically what that means is if we are ever going to leave the solar system and go and actually travel to other planetary systems and other stars and other planets, we got to get going a heck of a lot faster. But that's a story for another day. Voyager 2 is the only mission that has gone up to Uranus and Neptune. Just the once. So there's still a lot of mystery left in the outer solar system, out there, especially with Uranus and Neptune, because there's some things you can't do from here on Earth. There's some questions that you just can't answer from a distance. You've got to go up there. You've got to get up close and personal and look at things in detail. The Ulysses mission is, it's a satellite that studied the sun, but it passed by Jupiter in order to establish its orbit around the sun. So it got some data from the sun. The Galileo probe was in orbit around. It orbited around Jupiter for several years, and it got some nice data from up close. The Cassini mission was the big mission to orbit around Saturn. Cassini went into orbit around Saturn in 2004, and they just ended the Cassini mission a couple of years ago. So it was in orbit around Saturn, studying Saturn and the moons and the rings for almost about 10 years. Or a little more than 10 years, I think. So it got a lot of information. And then the New Horizons probe that I mentioned. The New Horizons probe is the probe that flew by Pluto a few years ago. But it also flew by Jupiter on its way out there and got some nice close-up pictures, too. The other big mission that is on this list that I haven't updated this in a little bit, but the most recent mission to go out to the Jovian planets is the Juno mission. Juno was a joint project between NASA and the European Space Agency, and it went into orbit around Jupiter just a couple of years ago. And so it's still, the Juno mission is still alive and kicking and still taking data, and we'll see some of that here in just a minute. That's about it. That's basically it. Compared to all of the times that we've gone to the Jovian planets, compared to all of the landers and the orbiters and the rovers that we've sent to Venus and Mercury and Mars and the Moon, this is it. We've only gone out into the outer solar system a handful of times to see things up close. And so, we're trying to do the best we can with figuring out what exoplanets are like. What are the terrestrial exoplanets like? What are the ice giants? What are the gas giants like? But we're making the best educated guesses we can. But we've only been to the outer solar system a handful of times. There are still big question marks left over with these big planets. So what can we say? Before we get into the weeds here, let's do a quick recap. Let's refresh our memories here. What do the terrestrial planets have in common? Right? What are the characteristics of not terrestrial planets, the Jovian planets? That's what we're talking about today. What are the characteristics of the Jovian planets? What do they have in common? What are they like? Well, the Jovian planets are big. They are high mass, but they're low density, right? They're much lower density than the terrestrial planets are. Why are they low density? Because they're made of mostly gas, right? The Jovian planets, they formed a primary atmosphere as opposed to the secondary atmospheres of the terrestrial planets, and they formed that primary atmosphere right at the beginning of the solar system. What are the atmospheres of the Jovian planets mostly made of? Hydrogen and helium, the two lightest gases. So that's why the terrestrial planets, there I go again. That's why the Jovian planets are so low density, because they're mostly made out of the lightest gases in the universe. What else do the Jovian planets have in common? Well, they all have lots of moons. They all have rings, right? Saturn has the biggest, most elaborate, most famous ring system, but all of the Jovian planets have rings around them. What else? They're all far from the sun, right? All of the Jovian planets orbit far from the sun. So if they orbit far from the sun, what else can we say about them? They have long periods. They have cold surface temperatures. All right. One other thing they have in common is they all have rapid rotation. They're all spinning very fast. The gas giants, Jupiter and Saturn, they have rotational periods. They spin once in 10 to 12 hours. The smaller ones, Uranus and Neptune, the ice giants, they rotate in about 20 hours. So they're all, think about it like this. Planets this big are spinning once in less time than it takes the Earth to spin. So they are moving real fast. All right. So with that in mind, let's look at them and see what else we can figure out, right? The Jovian planets. Remember how the Jovian planets formed, right? The nebular theory says the Jovian planets formed because a solid rock and ice core formed at the beginning of the solar system, and then it was that, mostly icy core that accreted all of that hydrogen and helium out of the disk to build up that big atmosphere. So the Jovian planets are mostly atmosphere, but they're not exclusively atmosphere. There's a solid core at the center of all of those Jovian planets. And when I said before, the Jovian planets have cold surface temperatures, well, what do I mean by surface? When you look at these planets, when you look at the planets here, you're not looking at a surface, right? This is not a solid surface that you can go walk around on. What you're looking at there is just the tops of the clouds. You're just looking at the top of the atmosphere. So when we study the Jovian planets, it's very hard to see what's going on inside the atmosphere because the clouds are opaque. We can't see through them. But we've got some tricks that can help us out. Right? What do we expect? what do we expect the atmospheres of the Jovian planets to be like? Well, they're made of gas, so we would expect the Jovian planets' atmospheres to behave like any atmosphere. How does any atmosphere behave? Well, here's a silly analogy for me to make, but the Jovian atmospheres are basically like a giant mountain made of pillows. Right? Because a gas is sort of like a pillow. You know, if you let a gas go, that gas wants to expand. It wants to puff out. It wants to maximize its volume, and be low density. So at the very surface, or rather I should say at the very top of the atmosphere, the gas puffs out. It's low density. It's low pressure. It's cooler. Right? What happens to a gas when you let it expand? It cools off. So the gas at the very surface, or the gas at the top of the Jovian atmosphere, it's low density, it's low pressure, and it's cool. It's cold because you let the gas expand. I say you let, like we're actually doing something to it. But the gas expands, and therefore it cools itself off. But also the gas is cold because the planets are far from the sun, so they're not getting a lot of sunlight. They're not getting a lot of flux of sunlight to warm it up either. But then as you go from the top of an atmosphere, as you go down, down, down into an atmosphere, the gas gets compressed by the weight of all the gas on top of it, right? The gravity, the mass, the weight of all that gas is pushing down on the gas underneath it, and it compresses the gas. And what happens to a gas when you compress it? It gets denser, it is at a higher pressure, and it gets hotter. So that as you go from the top of a Jovian planet's atmosphere, and as you go down, 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 that gas is getting compressed by all the weight on top of it. It gets compressed to become denser, higher pressure, and hotter. So when I said before that the atmospheres of the Jovian planets are cold, yeah, they're cold at the very surface. But once you get inside the atmosphere, it gets pretty hot pretty fast. And then something else happens. So if you were to do the math, right, which is a lot of what we can say about the insides of the Jovian planets is just done from figuring out the math to say, well, how does gas behave? How does gas behave when you compress it under such and such an amount of weight? Right? One of the ways that we can figure out what's going on inside of the Jovian atmosphere is just to say, well, you know, we can experiment with gases here in a lab, so we know how gas behaves, so let's do the math and let's figure out what we would expect it to be like. So the very tops of the clouds of Jupiter's atmosphere are, like we said, cold, low pressure, low density. And then as you go down, 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 my mouse going to behave? Okay, here we go. As you go down, 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 that gas, and the gas in Jupiter's atmosphere is mostly hydrogen, right? So as you go down through layer upon layer upon layer of the clouds, the hydrogen gets hotter and hotter and denser until eventually those hydrogen molecules get so compressed by so much weight on top of them that the hydrogen actually liquefies. It undergoes a phase change, so that hydrogen is actually liquid hydrogen. It's hot. You know, it doesn't liquefy because it cools down. The hydrogen here is still very hot. It's just under such an intense pressure that it condenses into a liquid. And then as you go down, down, down through the ocean of now liquid hydrogen, this is an ocean of liquefied hydrogen. As you go deeper and deeper and deeper, that liquid hydrogen is now becoming even more compressed, even denser, even hotter, until something else happens. Eventually, those hydrogen molecules are being compressed so tightly, they are being hammered by so much pressure that the hydrogen actually starts to conduct electricity. that those hydrogen atoms are so squeezed next to each other that electrons can hop from atom to atom to atom to atom to atom, and then electricity can flow through the hydrogen the way that electricity flows through a wire. When that happens, we say that that hydrogen has become metallic, which is the purple in this diagram here. Now, this is a little confusing, right? When I say the hydrogen is metallic, I don't mean it's solid. The hydrogen is still a liquid. It's still liquefied hydrogen. It's just liquefied hydrogen that is so high pressure that it can conduct electricity. Kind of like mercury. Kind of like, mercury, the element, right? The element mercury is a liquid that can conduct electricity. Right? That's probably what the hydrogen is like. Down there inside of Jupiter, that liquefied, electrically conducting hydrogen probably looks like mercury. Like the mercury in a thermometer or something. That's what most of the hydrogen inside Jupiter is like, actually. Because the pressure is so high down there, most of this hydrogen is actually the metallic hydrogen, not gaseous hydrogen. And then as you go down, 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 all the way to the center, eventually you'll get to the center of Jupiter where all the solids are. The rock and the ice is down there at the center. Inside of Saturn, it's very similar, except in Saturn, Saturn isn't as massive. Saturn's mass isn't as high as Jupiter's is. And so the gravity isn't as strong. The weight pushing down on the hydrogen isn't as strong inside of Saturn, and therefore, if the mass isn't as high, if Saturn's mass isn't as high as Jupiter's mass is, then more of the hydrogen is allowed to expand and be gaseous or liquid. You're going to get less metallic hydrogen because the gravity is just strong inside of Saturn, but you still end up with this big, icy, rocky core. If you do that math that I was describing, what you find is that, okay, here on the cloud tops of Saturn, or Jupiter in this case, here on the cloud tops of Jupiter, which is the part we can see, the pressure is about 1 bar, which is what's a bar, right? 1 bar is 1 Earth atmosphere. And it's about 125 Kelvin. So pretty cold, which is what we expect, and that's what we observe. But as you get down, down, down inside, the pressure becomes insane. 500,000 atmospheres, 2 million atmospheres, and the temperature gets really hot. And as you go down, 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 once you get to the bottom of the atmosphere of Jupiter, you're at the bottom of this giant ocean of liquid metallic hydrogen. The temperature is 20,000 Kelvin. So it's the temperature right there at the core of Jupiter is hotter than the surface of the sun. What did I say the core of Jupiter is made of? It's made of rock and ice. Ice. The core of Jupiter is mostly ice. Solid ice. But that ice is at 20,000 Kelvin. The ice inside of Jupiter is hotter than the surface of the sun. How does water and ammonia and methane and carbon dioxide, all of those other things that make up the ices, how can water stay ice at 20,000 Kelvin? And the answer is because the pressure is so hellaciously high. 100 million atmospheres. All of this weight is pushing down on the core, and all that pressure pushing down is keeping that water locked up in a solid state. Even though it's 20,000 Kelvin, the pressure is so high it can't melt. We've already talked in the homework about how Jupiter and Saturn are, where does it say here, right? Jupiter and Saturn we call the gas giants because, yeah, they have ice down there in the cores, but Jupiter and Saturn are mostly gas, mostly hydrogen. I mean, even though most of the hydrogen is liquid, it's still hydrogen. So even that's a little bit of a misnomer. Uranus and Neptune are called the ice giants because Uranus and Neptune are smaller than Jupiter and Saturn, and they're less massive because they didn't form as fast. Let me go back to the picture here, right? Uranus and Neptune formed further out into the solar system. They formed farther from the sun, where that protoplanetary disk, remember, all the planets formed out of that protoplanetary disk of gas and dust and ice. Uranus and Neptune formed slower. All that ice accreted together slower because they were way out there on the edge of the disk. There wasn't as much ice to accrete together. And so Uranus and Neptune accreted that ice slower, but eventually they did it. Right? Meanwhile, Jupiter and Saturn were off to the races. Jupiter and Saturn had already created their icy cores. They had already formed their icy cores, and they were pulling all that hydrogen and helium out of the disk to build this big atmosphere. Uranus and Neptune were like the late bloomers. They got a late start. And so eventually they did, though. Eventually Uranus and Neptune accreted that icy core, and they finally got gravity strong enough to start pulling the hydrogen out of the disk. And so they were going to do it, right? They were going to be Jovian planets. They started pulling in some hydrogen, pulling in some hydrogen. But then the sun came alive. And remember, the very first thing that the sun did when it became a star was it blew out a big wind, and that wind blew all the rest of the loose gas out of the solar system. So when, right, the sunlight and the solar wind blew away the hydrogen and helium out of the protoplanetary disk, and once all that hydrogen and helium blew away, there was no more gas to accrete onto the planet. So the Uranus and Neptune were only able to accrete this much gas, this much hydrogen, before all the rest of the hydrogen blew away. That's why their growth was stunted. Uranus and Neptune could only be ice giants, right? Why are they called ice giants? Well, because they're mostly ice. They're less gas. Their density, if you measure their density, which you did in a previous homework, right? Uranus and Neptune have densities closer to water than to gas, because they're mostly made of water ice, not gaseous hydrogen. Because Uranus and Neptune have less mass, their gravity isn't as strong, and they don't have enough gravity to compress that hydrogen into a liquid or a metallic state. All of the hydrogen inside of Uranus and Neptune should be gaseous. Do they have magnetic fields? Well, what do we expect, right? We talked a bit about magnetic fields in the terrestrial planets. What about the Jovian planets? What kind of magnetic fields do we expect there? Well, remember the dynamo theory. The dynamo theory says that a planet can create a magnetic field. A planet can generate a magnetic field if it's got rapid rotation, if it is full of an electrically conducting fluid, and if that fluid is hot and convecting, right? There's a lot of moving parts. You got to have the planet has to be full of a fluid, the fluid has to be hot and convecting, and conduct electricity in order to have electrical current flow in a loop, and the whole planet has to be spinning real fast. So what do we know? What do we know about the Jovian planets? Well, all of the Jovian planets are rotating fast. So all Jovian planets meet criterion 1. Right? They all rotate fast. In a Jovian planet, what is the electrically conducting fluid? What fluid can conduct electricity in a Jovian planet? It's not magma, right? In the terrestrial planets, the fluid that conducts electricity is magma, but they don't have magma. In a Jovian planet, the electrically conducting fluid is the metallic hydrogen. And all of the Jovian planets are hot on the inside, right? All of the Jovian planets are being heated by compression, right? All the gravity, all that weight pushing down on the gas compresses it to hot temperatures. So all of the Jovian planets are going to have convection. Hot gas is going to cycle up, cool gas is going to cycle down. It's happening in the metallic part, it's happening in the liquid part, and it's happening in the gaseous part. Hot gas rises, cool gas sinks. So you get convection all throughout the Jovian atmosphere, including right there at the cloud tops. So, what do you expect? Let's think about this like we thought about the terrestrial planets. Which Jovian planets do you expect to have a magnetic field? Which Jovian planets meet all three criteria? It's only Jupiter and Saturn, right? All four Jovian planets rotate fast. All four Jovian planets are hot and convecting on the inside, but only Jupiter and Saturn have metallic hydrogen. Uranus and Neptune only have gaseous hydrogen, and gaseous hydrogen doesn't conduct electricity. So, I said last time, the dynamo theory is the best theory that we have today to explain how planets generate a magnetic field. So, according to the dynamo theory, only Jupiter and Saturn should have strong magnetic fields. Uranus and Neptune should not. The problem is, you can't see magnetic fields from here on Earth. You can't point a telescope at Jupiter and see its magnetic field. You can't see the magnetic field of Earth either. How do you measure a magnetic field? You gotta go there, right? How do you measure a magnetic field on Earth? You do it with a compass. Here on Earth or out there in space, you measure a magnetic field by going up to the planet and using a magnetometer. A magnetometer is a device for measuring the strength and the direction of a magnetic field. So that's exactly what we did. Because one of the devices, one of the instruments that the Voyager probes had was a magnetometer. When the Voyager probes flew by the Jovian planets, they were able to measure what their magnetic fields were like up close as they were flying by the planet. And what do you find out? When you travel past the Jovian planets, you find that Jupiter has the biggest, strongest magnetic field of any planet in the solar system, which is of course what you'd expect because Jupiter is the biggest planet and it has a hell of a lot of metallic hydrogen. Saturn also has a strong magnetic field, right? Saturn's magnetic field is 600 times stronger than the Earth's is, because it's a big Jovian planet. And, Saturn has less metallic hydrogen than Jupiter does, but it still has a lot of metallic hydrogen. So it's got plenty of hydrogen, plenty of metallic hydrogen to make a magnetic field with. So Jupiter's magnetic field, Saturn's magnetic field, pretty much what you would expect according to the dynamo theory. But then you fly by Uranus and Neptune. And remember, the only time we've ever flown by Uranus and Neptune was with Voyager 2, and that was in the late 80s. That's it. So when Voyager 2 flew by Uranus and Neptune, what did they see? They found Uranus and Neptune have strong magnetic fields too. Uranus and Neptune each have a magnetic field 50 times the strength of Earth's. Which is a problem, right? Because Uranus and Neptune don't have any metallic hydrogen. They shouldn't meet the criteria of the dynamo theory. According to the dynamo theory, they shouldn't have any magnetic field at all, and yet there they are. Something weird is going on here. Something weird is happening inside Uranus and Neptune to make a magnetic field when the dynamo theory says they shouldn't have one. There's something else weird going on. According to the dynamo theory, remember, the dynamo theory requires that the planet rotate fast, that it needs to be spinning fast to make the dynamo, to make the magnetic field. And so when you do the math, you would expect that the magnetic field and the rotation axis of the planet should line up together. They should go together. And on Earth, you find it pretty well, right? The rotation axis of the Earth and the magnetic axis are about 12 degrees apart. right? The geographic North Pole and the magnetic North Pole of the Earth are like 12 degrees apart, which is, not lining up perfectly, but pretty well. On Jupiter, the North Pole and the magnetic North Pole are 10 degrees apart, pretty well. On Saturn, they line up perfectly. So Earth, Jupiter, and Saturn, those are the 3 planets whose magnetic fields are well explained by the dynamo theory. Uranus and Neptune's magnetic fields are totally dissociated from each other. The North Pole and the magnetic North Pole are 59 degrees apart on Uranus and 47 degrees apart. They're pointing in completely different directions. And also, they're off-center, right? The center of the magnetic fields. On Uranus and Neptune, the center of the magnetic field is not at the center of the planet. They're off-kilter. Which is not, again, not what you would expect according to the dynamo theory. So something is up here. Something else is generating these magnetic fields on Uranus and Neptune, and we don't know entirely what. This is still one of those, I put a question mark here on the slide for a good reason. There's still a huge question as to how are they doing that? How are Uranus and Neptune making magnetic fields? When you think about this for a second, you think, okay, Uranus and Neptune, we are fairly confident, do not have any metallic hydrogen. The pressure is just not high enough inside of Uranus and Neptune to make metallic hydrogen. So maybe it's not hydrogen. What if Uranus and Neptune are making their magnetic fields with some other kind of electrically conducting fluid, right? Uranus and Neptune meet criterion 1, they meet criterion 3. What if Uranus and Neptune are able to make a magnetic field with a different electrically conducting fluid that isn't metallic hydrogen? And you think, what fluid could there be inside of Uranus and Neptune that conducts electricity? And you go, well, pardon me, what about water? Right? We know there's water. Right? We know there's water inside Uranus and Neptune. It's at the core. It's frozen as ice, right? What if some of this water is liquid? What if it is liquidy enough to convect and carry electricity and complete the electrical circuit to make the magnetic field? There's a problem there. That water should not be a liquid. We looked at this before with terrestrial planets. Remember what this is. This graph here is the phase diagram for water. This is the diagram that tells you whether water is a solid, a liquid, or a gas for different combinations of pressure and temperature. Water cannot be a liquid above, well, this graph, now, the temperature is very hot, right? The temperature is very hot inside of Uranus and Neptune, and in fact, the temperature near the core of Uranus and Neptune is probably considerably warmer than 650 Kelvin. But this line here kind of keeps on going up until about a little less than 1 megabar. So imagine it's this line. It's pretty close to this blue line right here. Once you get above 1 megabar, the pressure is too great, the water stays frozen as ice. The pressure forcing down on the icy core of Uranus and Neptune is actually more like 5 or 10 megabars. So when, I put a lot of question marks on this slide and the previous one because, again, we can't see down inside these planets. We're doing the math and trying to figure out what must be going on. What do we predict? What do we expect to be going on? It is, even the most generous of predictions says the pressure cannot be low enough to let that water be a liquid. We think. So take this with a grain of salt. We think. So what could it be? If it's not liquid water, what could be conducting the electricity? That's still a question mark. That's still a big mystery. Let me say one thing as an aside. There was an interesting experiment that came out a little over a year ago. Some chemists were playing around with water crystals at high pressures. So all of these Roman numerals here, right? 11, 1, 1, 9, 15, 8. These Roman numerals are different kinds of water crystals. Right? When you take water molecules and you exert different combinations of temperature and pressure, those water molecules can lock together as crystals, but the geometry of the crystal lattice is different. And so if you have different shapes of water crystals, they give them different names. You know, ice 1C, ice 1H, ice 9, ice 15, ice 8. So these scientists, a year or so ago, were playing around with taking ice and exerting really high pressures on them to see what would happen. And they were testing the shape of the crystals. And when they started creating ice 7, the crystal started looking like it would conduct electricity. Water, ice, solid ice crystals that they appeared in this experiment to be acting like they conducted electricity. Like electrical current could flow through the crystal. Now, maybe this is the answer. Maybe this is the answer to the mystery. There may not be liquid water inside of Uranus and Neptune, but maybe some of this ice, here, right? Maybe some of this ice, solid ice in the core, maybe some of this ice is ice 7. And maybe ice 7 crystals can conduct electricity, and maybe this is the electricity that generates the magnetic field. We know there's a magnetic field. We've seen the magnetic, well, we haven't seen it, but we have detected, we've measured the magnetic fields of Uranus and Neptune when Voyager 2 flew up next to them. We just don't know where they're coming from. This is still a big mystery. Why am I hammering on about this? Why, this is this just me nerding out about something, or is there a bigger point that I'm getting at here? A little bit of both. But these are two planets, the ice giants, right? Uranus and Neptune. But they're not. Because remember when we were talking about finding exoplanets, right? When you find exoplanets with the Doppler method and the transit method, we have found a lot of ice giants, right? Of the thousands of planets that we found using the Kepler Space Telescope and TESS and the Doppler method and all of that, out of the thousands of planets, out of the thousands of exoplanets that we've discovered a lot of ice giants. And yet, one of the basic questions, like, what's it like inside an ice giant? What kind of ice are we talking about? Does that ice, is it ice 1 or ice 11 or ice 9 or ice 7? Here's the thing. When you do the math, when you do a bit of a back-of-the-napkin calculation on what the pressure should be like inside of Uranus and Neptune, when I do the math, my little back-of-the-napkin calculation says actually the pressure in the core, the pressure at the core of Uranus should be more like ice 11. And I don't think anybody has an experiment where they've seen ice 11 conduct electricity. That one experiment last year was talking about ice 7. Does ice 11 conduct electricity? Not that we know of. And yet, unless I'm doing the math wrong, and well, me and everybody else that studies these planets, right? Unless all of our models for what the pressure inside of Uranus or Neptune are like, they should be more like ice 11, right? The pressure is more like 8 megabars up here. So what are these planets like? What is it like inside of Uranus or Neptune? How are they making the magnetic field? We don't know. We've got some ideas, we've got some guesses, but the guesses don't all agree with each other. So what's up? And to get to the bigger, more important point here, if we're not sure what's going on inside of the two ice giants in our solar system, what are these hundreds of alien ice giants like that we're finding? Because if we don't know about the ones that are in our own backyard, we sure as heck don't know what's going on with these alien ones, and we've found hundreds of them. So there's still a huge question mark hanging over our heads. There's still a big set of mysteries. Not just this one mystery. There's a big set of mysteries left there in the outer solar system, trying to figure out what these planets are like. I said several minutes ago, you can't see a magnetic field in a telescope, which is true, but you can see the effects of a magnetic field. Because when a planet makes a strong magnetic field, that's when it has aurora, right? The aurora borealis and the aurora australis on Earth are caused by charged particles from the sun. When you've got charged particles from the sun being grabbed by a planet's magnetic field, and they get sucked, the magnetic field of the planet sucks them down, and those charged particles slam into the atmosphere, and when those charged particles from the sun slam into the atmosphere, it causes the atmosphere to glow. That's what the aurora are here on Earth. The aurora here on Earth are charged particles being grabbed by the magnetic field, hitting the atmosphere and making the atmosphere glow. And we find really bright aurora on Jupiter and Saturn. Here, these pictures are taken from the Hubble Space Telescope. So these pictures are from here on Earth, or in Earth orbit. Hubble's in Earth orbit. These are pictures in the infrared, right? This picture here is visible light, but these pictures of the aurora and these pictures on Saturn are infrared images. So you can see down there inside the layers of the atmosphere is glowing near the North Pole and the South Pole. So you can see the magnetic field because you can see the strength, you can see the effect that strong magnetic field has by creating the aurora. This is the only picture ever taken of aurora on Uranus. Because A, Uranus's magnetic field isn't as strong, and Uranus is farther from the sun, and also the solar wind is pretty weak out there. So normally Uranus and Neptune don't have aurora. This picture just so happened to get taken when Uranus got hit by a solar flare. And so when Uranus got hit by that solar flare, the charged particles from the sun, from the solar flare, got grabbed by Uranus's magnetic field, and it slammed into the atmosphere, and so those charged particles hit the North Pole, and they hit the South Pole. Remember from us talking weeks ago, Uranus is the planet that's spinning on its side, right? Uranus is rotating 90 degrees with respect to the ecliptic. So here's the North Pole. Here's the North Pole of Uranus. Here's the North Magnetic Pole. Here's the South Pole. Here's the South Magnetic Pole. It's off kilter and it's off center, just like what Voyager 2 measured. Right? We've only got one close-up measurement of the magnetic field of Uranus from Voyager 2, and that was in the late 80s. And so you'd be forgiven for thinking, well, maybe it was a bad measurement. Maybe your Voyager 2 was giving us bad information. Nope, apparently not. Here's the North Pole, here's the South Pole. You can see it from the aurora, just the way Voyager 2 measured it. Like 59 degrees apart and off center. No picture like this has ever been taken of Neptune. Oh dear, wow, that got sped up way faster than I expected. The other interesting point, I mean, another interesting point about the atmospheres of these Jovian planets is the weather patterns. Because, you've got these planets. These planets are mostly atmosphere, and they're moving extremely fast. Right? You've got these planets that are spinning in less than 24 hours, which means those wind speeds are hellacious. And when I set up this graphic, it was going slower, so it was easier to see. But somehow they got sped up. I'm not sure how. Okay, here's another picture, close-up picture. Here's a little better illustration. Okay. My apologies for the, confusion. But here is a little bit of a movie put together from images of Jupiter taken by the Cassini probe. Remember, Cassini was the probe that went to Saturn, but it flew by Jupiter on its way out to Saturn. And it made this bit of a movie. Here's the whole surface of Jupiter sort of unrolled like a map. And you can see, for all of the reasons that the homework points to you guys, the wind is blowing, the planet is spinning really fast, which means the clouds are moving really fast, but also the clouds are convecting. These clouds are upwelling. They're heating and lifting up, and then they're cooling off and they're sinking down. So there's a lot of motion. There's a lot of three-dimensional motion. The wind here is blowing east to west, while it's also migrating north-south. You can actually see it from here. Some of these clouds are actually moving northward or southward as the whole planet is spinning eastward. And the clouds are also moving inward and outward. They're moving away from the center and toward the center as all the clouds are convecting. So all of this three-dimensional motion happening very fast creates these really complicated storms and wind patterns. This is what creates the red giant, right? The red giant is basically a giant hurricane because the clouds up here are moving westward, the clouds down here are moving eastward, and when these two winds blowing in opposite directions collide with each other, it's the exact same thing that happens here on Earth. Wind blowing in one direction and wind blowing in another direction meet up with hot air rising and convecting upward. It creates storms and hurricanes. And that's what all these little, not just the red spot, all of these little knots, all these little circles and ripples here are storms. They're hurricanes. Just like on Earth, very much like on Earth. I promised you the new cool pictures, and here are some of them. This is the red spot from the Juno space probe. Juno is the newest probe that went into orbit around Saturn just a few years ago. Here's a close-up picture. There are times when Juno is orbiting very close to the surface, or to the cloud tops, I should say. And so it's getting some very close-up pictures. Some of these pictures are true to life. So here is a picture of what the red spot looks like if you could see it with your naked eye. Notice it doesn't look the same as it looks when it's all, when you're viewing it from far away. There's a lot of detail here. These planets are huge. And just like when you're looking at clouds on Earth, right? When you look at clouds on Earth, the more attention you pay, the more detail you can see. And so when you get to these planets and look at them close up, you can see levels of detail, how the wind is blowing. You can see the three-dimensionality here. Look down here. You can actually see some shadows. The clouds are casting shadows on the clouds next to them. There's depth here. The thing that you don't see, the thing that's hard to notice when you're looking at these planets from far away, is it all just looks like one perfectly round ball. It's not. There are layers to these atmospheres, and there's depth and there's detail that you can only see when you get really close. Here is another picture of a cloud layer, and here you go, right? When these wind wind blowing in one direction collides with wind blowing in the opposite direction, and where these two wind patterns collide, they spin off all these little red spots. All of these little red spots are tornadoes. They're hurricanes. They're storms. You can really see detail when you turn up the contrast. So a lot of pictures of Saturn, or sorry, Jupiter here, a lot of these colors are enhancing the color so that the details really pop out. These colors here, you know, it kind of looks, Jupiter kind of looks all coffee colored. When you really turn up the color so that all the details get exacerbated, you can really see what's going on. This is the North Pole. This is looking down on the North Pole of Jupiter here. And all of this wind is blowing counterclockwise, like all the planets rotate. Well, like most of the planets rotate. And all of this circling, convecting, rising and sinking, and blowing wind constantly spins off these twisters, these hurricanes, these tornadoes. All of these images, the next few images, these are all color enhanced. So this is a good lesson in astronomy, or just when you're interested in astronomy, is, you know, when you see a picture that looks too good to be true, you know, when you see a pretty picture online or in an astronomy textbook, read the fine print, right? Sometimes these pictures are made to be true to the naked eye, and sometimes they've been color enhanced, or they've been color coded so that they give you more information. So it's not just done for aesthetics, although sometimes it is done for aesthetics. But sometimes these images are enhanced to better than the eye could see them, to give you more detail or more information. So, you know, always read the fine print is what I'm saying. So these are color enhanced. And here you can really see the detail here. Notice, as you zoom in and look at smaller structures, what do you notice? You notice that there are even smaller structures, right? One big storm spins off a bunch of even smaller ones, which is kind of like what happens here on Earth, right? When you have a big hurricane, blowing through the Atlantic Ocean, that big hurricane can spawn off a few other smaller hurricanes. Or when that hurricane hits landfall, when it hits the coast, it can spin off a cluster of tornadoes, right? And you can see the three-dimensionality here. Look at these clouds over here, or these clouds over here. They're casting shadows. You can tell that they're lumpy. There's texture, there's depth, right? Some of these clouds are happening on the surface. Some of these clouds are happening underneath. The white clouds sure look like they're on top of the blue clouds, which is actually exactly what's happening. These colors tell you composition, right? Why are these clouds made of different colors? Because they're different kinds of clouds. They're made of different chemicals. And also, they're telling you depth. The white clouds all look like they're on top, and that all these other colors are underneath them, because that's what's happening. When you're looking at Jupiter, the white clouds are made of ammonia ice. The red clouds are made of ammonium hydrosulfide, and they're reddish in color. And the clouds underneath them are the bluish clouds, and they're made of water ice. So when you look at these clouds and when you see different colors, you're not just seeing different pretty colors, you're also seeing depth, and you're seeing chemical composition. That the white stuff is on top, that's the ammonia. The red stuff is underneath that, that's the ammonium hydrosulfide. And the blue stuff is on the bottom. And so if you're seeing a blue layer here, or if you're seeing a big blue hole, that is literally a hole. There's a hole in the white clouds, and since there's a hole here, it's letting you look down through the white layer into the blue layer. The reason why you can see, the red spot here, right? Why is Jupiter's red spot red? Because What you're looking at is the eye of the hurricane. You're looking at the eye of the hurricane where, since there's no white clouds here, you're able to look down through the white layer to the red layer underneath it. And the white stuff is up above that on the surface. But also, Jupiter's gravity is so extreme. The pressure is so great that all of these layers are squashed. Oops, pardon me. These layers are squashed so that each of these cloud layers is denser and more opaque, so that you can see them. They look more solid. These cloud layers look more compressed, more opaque, more solid, so that you can see like a clear white layer, a clear red layer, a clear blue layer. Saturn is not as massive. Saturn has weaker gravity. And therefore, since Saturn's gravity is weaker, those cloud layers they're allowed to puff out and expand. And so on Saturn, the cloud layers are thicker but hazier. So that's why when you look at Saturn versus Jupiter, right? Jupiter, you can see a lot of details because those dense, thin clouds are stacked neatly on top of each other. On Saturn, Saturn looks hazier, it looks fuzzier, it looks less detailed because the cloud layers are thicker and puffier, and you can't see as much detail through the layers on Saturn as you can through Jupiter in the visible spectrum. If you want to see what's going on inside Saturn, look in the infrared. Because if you're looking through the infrared, you can see down through the cloud layers, and what do you notice in the cloud layers on Saturn? It looks very much like Jupiter. These stripes, these bands of clouds going in opposite directions, spinning off storms, right? Here are the polar regions on Saturn, and you can see sort of a vortex of wind blowing and spinning off storms neatly near the poles of Saturn also. So a lot of the same storms and dynamics going on Saturn as are on Jupiter, but you gotta look through the haze to see them on Saturn. Uranus doesn't show you as much. And one of the reasons for that is that Uranus is the planet that rotated 90 degrees, right? When this picture and this picture are basically the same picture. When these pictures were taken close up by Voyager 2 when it flew by in 1986, here's the North Pole. Or maybe it's the South Pole. I don't know which. But here's the pole, right? Here's the pole pointing toward the sun. And so since Uranus is spinning like this, as Uranus spins, it's always pointing toward the sun. The sunlight is always shining down on one face, which means this side of Uranus is getting pretty even heating. There is no daytime and there is no nighttime. It's always daytime because as Uranus spins, this side is always facing the sun. The dark side of Uranus here is going to be the nighttime side, and it's always the nighttime side. So that during summer and winter on Uranus, the weather is very boring. One side is always daytime, the other side is always nighttime. One side is always warm, the other side is always cold. There's not a lot of even though the wind is blowing fast, this wind is always warm, this wind is always cold. You don't get as much of the convection and the cloud layers crashing into each other during summer and winter. But then 20 years later, or in this case 13 years later, now by the time 1999 rolls around, we've got the Hubble Space Telescope. 13 years later, now it's springtime. And now with springtime, Uranus is getting more sunlight hitting the equator. Now you're getting daytime and nighttime happening once per rotation. Now you're getting the sunlight shining down on the equator, which means you do have hot clouds and cold clouds and hot wind and cold wind crashing into each other and spinning off storms like these hot spots right there. So the weather can change pretty dramatically between summer and spring and winter and fall on Uranus because it's got such an extreme tilt, right? Earth is pretty temperate, right? The weather doesn't change that much between summer and winter here on Earth because Earth is only tilted 20 degrees. When you're tilted 90 degrees, like Uranus is, the weather varies extremely from summer to spring to winter to fall. Neptune, this is the first, this picture here on the left is the first good picture of Neptune that was ever taken. This is the picture that was taken close up when Voyager 2 flew by Neptune in '89. And it turns out something that no one had ever seen up to then from here on Earth. Neptune also has a big hurricane-type storm happening. They called it the Great Dark Spot, to go with Jupiter's Great Red Spot. Funny thing is, so they thought, when in '89, when these pictures came back from Voyager 2, people thought, maybe these giant storms are common on these Jovian planets. Maybe they happen all the time. And, for that matter, maybe they last for a very, very long time. Because Jupiter's red spot has been there since Galileo discovered it. Galileo discovered Jupiter's red spot in the early 1600s. So that tornado, that hurricane, that storm, the storm that is Jupiter's red spot has been there for 500 years. 400. But 400 years. How long do these storms last? Are they permanent? Do they last forever? Or are these giant storms, do they last for centuries? Jupiter's red spot has been there for centuries. And so in the 80s, people thought, maybe these giant storms that last for centuries are common among the Jovian planets. But then, over the course of 10 years, it's gone. When they came back and took, or over the course of about 10 years, the Great Dark Spot got smaller and smaller, and then here's a set of pictures that were taken of Neptune from the Hubble Space Telescope. Again, these colors are, these pictures here are color enhanced, so these are not, there isn't this green ring on Neptune. This is what Neptune looks like to the naked eye. But yeah, by 1998, it was gone. So maybe not, right? Maybe these giant hurricanes, maybe they do last for centuries, like the red spot has. Maybe they don't last that long, like the Great Dark Spot. They're clearly not permanent, right? If the Great Dark Spot could go away from being this big to being totally gone in 10 years, maybe the Great Red Spot will eventually end. Maybe that storm will eventually fizzle out. And in fact, that might be what's happening right now. Because one thing that we've noticed especially over the last few years, because we've got really good images of the last few years, but when you compare Jupiter from in the 70s to the way it's been in the last few years, the red spot is getting smaller. We've been noticing this steadily for decades, but it's especially been noticeable in the last few years that the Great Red Spot is getting smaller and smaller and smaller. Now, does it always go in one direction? Maybe the red spot is getting smaller and it's going to get bigger again. Maybe. Or maybe this is a sign that the red spot is eventually going to end. Hurricanes eventually end on Earth. Maybe these things, and clearly these storms end on Neptune too. Maybe that's a sign that, here over the next, who knows, 100 years? Maybe over the next century, the Great Red Spot will shrink, die out, be gone. And then maybe another storm will grow in its place. Who knows? Right? Apparently these features don't last forever. That's the thing about Jovian planets, right? When you've got a planet where the surface features are not a surface, they're just the top of a rapidly moving, rapidly evolving atmosphere where the wind is blowing at hundreds or thousands of miles an hour and crashing into each other and spawning storms and lightning and these planets can evolve. The surface features of the planets, as far as we can see them, can evolve on very fast timescales, much faster than on a terrestrial planet like Earth, right? Here on Earth, it takes millions and millions and millions of years for the surface to change noticeably. On the Jovian planets, the surface features can change in just a matter of years because it's moving just that insanely fast. There's a reason why, even though the Galileo probe was orbiting around Jupiter for years, the reason why we sent Juno is because there's still a lot of questions left about what these things are like, how they work, how they move, how they evolve. The next big mission, hopefully, there are several missions in the works that hopefully will get off the ground here in the next 10 years. We need to get back out into the outer solar system again and again. We've only gone there less than a dozen times. There are also, as I've mentioned, lots of moons orbiting around the Jovian planets. What are all they like? We've only really studied some of the moons in detail. We've only studied a few of the moons in detail. What about the other couple of hundred moons in the solar system? What are they like? And then we want to get back out to Uranus. Because there are so many questions left about how ice giants work. And now that we've discovered a few hundred other ice giants orbiting around other stars, that really has reignited the fire of saying, we got to know how these things work. So there's the beginning of a couple of missions. One mission to go and land on Europa, the moon of Jupiter, and another mission to go into orbit around Uranus. These things, when these missions get built, right, it takes years to design and build a mission like that. Because when NASA builds something, they build it to last. And so it's not only going to take years to build this thing, it's also going to take years to get out there. Because once you get out into the outer solar system, things are really far apart. And it takes years to travel out to these outer planets. So this is going to be news for the next few decades. What are the Jovian planets like? What are their moons like? What are their rings like? Hopefully these missions will get launched here in the next 10 years. And then it's going to take 10 or so years to get out to their targets. And then they're going to go into orbit around the planet. And if this mission actually happens, if a mission goes into orbit around Uranus, hopefully it'll stay orbiting around there, studying it for years and years and years. And at this point, we're talking about, this mission from conception to completion could be the work of 30 or 40 years. And I strongly suspect that if and when we finally do that, a lot of mysteries are going to get solved. We know so little about how the ice giants work that if we learn a few things, those are some huge answers. And of course, as usually happens, when you answer one big question, that only tends to spark a bunch of more questions. So this is part of the next big frontier. We've studied the terrestrial planets dozens of times. We know a lot about how Earth, obviously, and Venus and Mercury and Mars, and the Moon, how they work. But when it gets to the outer planets, the Jovian planets, especially the ice giants, we know a lot. And we've got a lot of educated guesses. But all of those planets and their moons and their rings and the comets and all the things that are out there in the outer solar system, they are a great frontier that has yet to be fully explored. And if all goes well, they will be explored, and we're going to learn a lot of things for the rest of our lifetimes. So, watch this space.